Hey everyone, it's Sean. Welcome back to the channel. Got a fun little video for y'all here today. I think I made mention that I'll include occasionally some things from work, so you can see some of the stuff that I do daily. What I have in front of me is a telephone and radio switching system. You can look this up online. It's called an enhanced terminal voice switch. I won't get into all the history of the switching system, but it's typically used in air traffic environments to allow ATC controllers the ability to select up AM modulated radios for communicating with aircraft or different type of direct access lines, telephone intercom circuits, etc. Okay. Now in the classroom environment, you're going to have something like students, which is not currently populated in this room, so I have some free time to kind of show you something. And when you've got students, you tend to want to be able to, in an efficient manner, demonstrate certain things, like if I hit this key, what is it going to do? If I hit this key, what is it going to do? Or if I select up this line, what is it going to do? Okay. And the easiest way to do that is to get it up onto something like a smartboard or a device somewhere to where everybody can kind of see things without being crowded around a small screen. Okay, so that's what I've done, and this is what I'm going to demonstrate for you in this video. All right, I'm actually through determining where my video feeds are at my position here, been able to determine where within my video signals are at, so I can take this position here and the devices I have attached underneath, take it out to a monitor at a distant end for demonstration purposes. Here, let me zoom in. So right now I'm at the position. If I hit the frequency key, you see right up there on the board, that changes over. Transmit, frequency, you can see those changes. If I hit a telephone circuit, you can see that change happen right there at the smartboard. Now eventually, because this is a smartboard, I do plan to figure out a way to make it interactive from the board for demonstration purposes. But for now, getting a video feed from one of these positions over there, that really helps out with the training environment. There are a few things that I have to consider, and I'll open up the board and I'll walk you through it. Because this is a system that's used and managed by somebody, I don't want to go into this this device called a PIP, go in here and to modify the system in any way that is unsafe. I don't want to make changes inside of any device, i.e. this or the PIP or even the cables themselves. I don't want to modify things as they exist. Okay, I want to keep them remaining the same. So you might start asking yourself, well, how did you make this happen? Because you have to modify something. I'll show you that here in a minute. But first, let me cover some theory with you. Okay, this device right here is a single board computer, and it manages all the video and audio and touch entry functions for my position equipment. Okay. And so what that means is that without this device, I can't use this module right here, which controls volume at, say, a handset or a loudspeaker. Cannot control illumination at my position equipment. Okay. Nor will, and then there goes the loudspeaker. Nor will I have an interface from the headset, jack box. All that's got to communicate, or the TED. All that's got to communicate with this device here. Now, inside of this device, if I were to break it open, you would find a microprocessor, CPU. You would also find an onboard graphics card. I believe the processor is an AMD, and then it's the video graphics. It's not really a graphics card, it's not standalone, it's a GPU on the single board computer, riding I believe a PCIe style bus on the physical computer. So what does that mean? Well, that means that at the output cables for my touch entry display, okay, now I've got two cables, TED data, TED power, and actually over the power there are two wires that carry our resistive membrane carry feedback from this for selection information. Okay, I'm not going to focus on this one for now. I'm going to focus on this. The TED data is what's going to carry my red, green, and blue horizontal and vertical sync. Okay, but it does it in a very interesting way. So it taps off that information from the GPU. Okay, and then it's going to provide it through various ICs. Actually, a handful of ICs. We call them quad diff ICs. You can look them up. There's several pins, and then what they do is they take that RGB, red, green, and blue, and say I'm just looking at the red at one input on this IC. It's going to provide me two outputs based off that one input. One output is going to be at the same amplitude as the input, at the I guess you could say probably same phase, even though that's not really correct. The other one's going to be an inverted output. Okay, so think of this. Let's say that I have a signal that comes in that's a kind of a square wave. Okay, you see how I'm drawing this pattern up, over, and down? Well, at one of the outputs I'll have a signal that looks exactly the same, up, over, and down, at the same amplitude, at the same rate, so it's at the same frequency as well. Okay, then the other one, instead of it going over, up, and down, it's going to go over, down, and up. That's the inverted signal. Hey, it's still at the same amplitude, but an inverted amplitude. We'll say, just for throwing a number out there, this amplitude was let's say a 3-volt peak. Bottom amplitude would be at a negative 3-volt peak, if that makes sense. Okay, and what you actually do is you take like your red signal for your video, you send it through 3 different comparators, and thus you have 3 outputs of red and the same as their input, and then 3 inverted outputs of red, and then you do the same thing for the green, and then you do the same thing for the blue. Then you kind of do the same thing for your horizontal and vertical sync. Now, the way this video feed is used is kind of very similar to what you had in older medical equipment that made use of a KVM, say a little thingamajig set beside your bed that measured your heart rate and etc. There'd be a device and then a cable going to the monitor per se. It's old monitor technology. You're going to have red, green, and blue over a DB25 cable. Yes, that's DB25. Typically, you would refer to that as a serial data cable, but not in this instance. It's being used as to provide multiple video feeds and horizontal and vertical sync. So, barring where you've worked in electronics industry, you might have seen something like this on medical equipment. Now, here's what it does. It takes those 3 reds, 3 greens, and 3 blues, and stacking them together to create color saturation on this display. And then it's using the inverted signals and stacking them together to create color saturation on the display. Okay. Now the display itself is only 480p. If you were to look at the signals and everything, you'd be able to determine the lines. You'd be able to determine that this is essentially a 480p display unit. Okay. And then again, the horizontal and vertical sync. The horizontal sync, if I'm not mistaken, I typically get these backwards. If I do, I'll correct myself later on. 15 kilohertz on our horizontal sync, and then 48 hertz on our vertical sync. As a matter of fact, here in a few minutes, we'll see that itself. Okay. So what I want to do for now is I want to take, of course, modern TVs. This is one thing we're going to discuss. They don't like that 15 kilohertz signal. You don't have that anymore. You're looking primarily at 48 hertz or 60 hertz or something along those lines to 120 hertz, whatever the refresh rate is of that monitor TV. That's essentially what we're going after nowadays. Older stuff, yeah, and older monitors made use of that, but I had to do some conversion. So anyways, that being said, what I'm going to do for now is I'm going to move this out of the way, because I just use this for demonstration purposes to discuss the purpose of the PIP with my students. But I'm going to take this TED out, and we are going to look at those signals using an oscilloscope. Okay, so I've got this pulled out and a cable in a box. Okay, actually 2 cables. I've got a cable that goes from the PIP that's down there, running into one side of this DB25 breakout board, then the other cable coming out going into the TED. This is what I work on to get those signals in order to feed them off, but I got to give several considerations. Okay, so what I got to do is I got to make sure that when the signal is fed through here and then it's come to the other side, this touch screen acts as a load, and if that load's there, then I can't also get it over to the display because the signal amplitudes decrease significantly. So what I have to do is I have to tap off one of the red, one of the green, one of the blue, a horizontal and a vertical sync signal, and then I've got to pipe it to basically a video splitter. Those of you who are old enough, y'all remember these devices. What was it taken? VGA usually had like 2 or 3 different formats. It had a RGBHV, which is what we're using here, RGB, red, green, blue, horizontal, vertical sync, or it had RGBS, which was combining your horizontal and vertical sync together into one sync signal. And then there was a third option. I can't really remember what it is off the top of my head. Those of you can, at least a third option, you can scour the internet. Okay, look for it for yourself. Now, for demonstrative purposes, I've already mapped it out, but we'll look at these together. Here goes my DB25 plug. Pin 1 through pin 3, that's all my red signals. Pin 4 through 6 is all green. Pin 7 through 9 is all blue. Then I got vertical sync at 10, horizontal sync at 11. Now down at the bottom, okay, we have pins 14 through 16. That's going to be the inverse red signals. 17 through 19. 17, 18, 19, that's the inverse green signals. 19 through 19, 20, 21, 21, or excuse me, 20 through 23, that's his. 17, 18, 19, 20, 21, 22, 22, 23, there we go. 20 through 22, 20, 21, 22, again, dang, stumbling over my words, is our inverse blue, with 23 being vertical sync, the inverse vertical sync, 24 being the inverse horizontal sync. So let's look at those signals underneath an oscilloscope. All right, let me first look at my red information come on and off of one of the pins. You can choose 1, 2, 3. You can see that data sitting here. It's not really data per se. This is an analog signal. If I take and adjust my scale, we can break it down, see that information flow a little bit better, how this signal is repeating. This first signal, I want you to take note of it. This is our sync, part of our sync, horizontal vertical sync. As a matter of fact, if I bring this up, see, barring where I trigger, we can make that a bit clearer. This is all the red information. This is analog red signal. We can see that that strongest peak repeats itself with the signal coming through. All right, so that's our red. Let's look at the green. I'll take that back. The next one is blue. That's on pins 3 through 6. You choose any one you want, and again, you can see the highest peak there. We'll see that again here with our sync signal. Hopefully this will make sense to you. There you go. Expand it out. Yeah, this is all my blue data. Okay, you can see that that information is repeating itself. Okay, we get a little lost in the weeds if we try to trigger at the baseline. So if you're triggering, trigger towards the peak of the signal. Okay. Now we'll look at our green signal. So this was blue. Let's look at green. Here's our green. We see we got quite a bit of different information sitting here. Again, this is a green signal. If I come and expand it out, you can see that the signal still repeats itself. Trigger on the top, we can come in. We still kind of see that first peak sitting right there, or where I'm triggering it, but we got other information coming over on green. You can look up these signals online and get any more information, but I know based off of what I'm seeing, what I am looking at here. So next, let's look at our vertical sync signal. So I'm looking at my horizontal sync signal first, and yeah, I'm glad I said that. I get these confused sometimes. Yeah, the horizontal sync is actually a 25 kHz sync signal, not a 15 kHz. Okay, now if I was to, let me turn the menu off. Let's see. Let's span this out a bit. Oh, no, wrong way. Wrong way. Let's go the other direction. Oh, yeah. Span it out this way. Here we go. Here we go. There we go. Let's try to trigger it. There we go. You can see that sync pulse right there as I've spanned it out. Better triggering on the bottom half of that lobe, but there you go. There goes the horizontal sync signal. Now let's check our vertical. And coming off of pin 10, pin 11 was our horizontal sync, pin 10 is our vertical sync. You can see that nice pretty signal right there, and I did have that one right. 48 hertz signal. Okay, trigger where it's best for you, but you can see that as I spin it out, you can see you can get more on the screen or less depending on how I span. I'm more interested in those peaks, but I know when I'm seeing this that I am looking at my vertical sync signal. So we have RGB and we have horizontal and vertical sync. So now, for all intents and purposes, I actually have to tap off 23 and 24 for my horizontal vertical sync, because what I do is I have, this is where I did the modification on the back side. There goes the input. That's all good. I tap off of an RGB, the horizontal and vertical sync, and additionally I got one more thing I'm tapping off. I'm tapping off a ground, providing it to this right here. Now on the other side of this cable, I cut the traces, because what I'm going to do is I'm going to send that into this video splitter. Then at the output of the splitter, it's going to feed back into the other side of this cable. So that way I can go off the DB25 directly into this display here. And then the other output will run over all the way to a device I have over my monitor. So before I discuss that, I'm going to go through a little slide with you for a few minutes. All right. Let's first begin with the PIP to VGA conversion breakout board diagram. Okay. Primarily here you see the DB25 connector coming from the PIP device, the output DB25 connector, breakout board in the center. Okay. Typical pin topology: pin 3 of DB25, breakout board to pin 1 of DB15 VGA. What is this showing is, this discussion over here is the pin-to-pin comparison from going off the DB25 connector down to the VGA that's going to this VGA splitter that I have at the very bottom. Okay. So if you need to take a second to look at those pins, encourage you to do that now. Pause the video and look at those pins if you need time to. Okay. So as this is fed into the VGA splitter, keep in mind I mentioned that all these traces, as they go to the other side of the breakout board, for the RGB horizontal and vertical sync, I break those. Just, you know, make a break in the trace itself. I don't do that for the ground pin coming off of pin 13. That ground pin, the trace is left alone, and it is soldered into or tapped into, terminated into the VGA plug that I feed into the input of the VGA splitter. And then pin 13 at the other end, you see this VGA DB15 plug. This is one of the outputs feeding back into that DB25 breakout board and over the DB25 connector. Now note, this right here just mentions about the breaks. That way, if you were to follow it, you could do the same thing. Not saying you ever would, because how many of you are actually doing this in your spare time or working on this kind of equipment? All right, neither here nor there. Yeah, so VGA splitter is going to have two outputs. One, I'm feeding back into that DB25 connector. Now keep in mind these other pins are carrying red, green, blue, and the inverses, and a additional horizontal and sync signal. I'm not touching them at all. Those traces are left intact. So all I'm doing is modifying this breakout board to take a portion of that signal, split it, and then pipe it right back into the other side. And then because I have an additional VGA output, I use a VGA DB15 cable that's going to go to an OSSC, which you can order one of those right off Amazon for a couple $100. Again, here's the pin topology, what they represent as far as color, and ground and vertical and horizontal sync. By all means, pause and read this information right here if you need to, if you were ever going to do the same with a similar device. All right, here's a visualization slide. I'm not going to spend a whole lot of time on this. As a matter of fact, I didn't even include the right horizontal vertical sync signals off of a older analog oscope. Were these digital? I can't remember. But you saw the same signals on our digital phosphorus oscope, so there's no point in me repeating any of that. As you can tell, I had a lot of testing in this video. I'll throw up other pictures. I built some of my own circuit boards as well to attempt to, instead of using a VGA splitter, I attempted to do some similar things with my own designs. And with some decent success, given when I was first initially piping this over a projector versus that smartboard. Yeah, I did use a projector first, and my circuit designs worked great for it, but I needed some additional things to make it work with the smartboard, so I decided just to scrap my designs and go with something that I can buy online without having to build a whole lot of my old stuff. And this is just continuity of how I ran everything underneath the console itself. Here's the OSSC. Like I said, you can buy one of these off Amazon. It costs you a couple $100, I think, somewhere between $100 $200. I can't remember. They're a bit expensive, but you can see here the basis of what the OSSC is going to do for me. Okay, it's taking that VGA RGB horizontal and vertical sync signal. It's in a 4:3 ratio. The actual lines, if you were to look at your scan lines and tally them up or whatever, actually you are a 640x480, which is 480p signal with a horizontal sync of 25 kHz and vertical sync of 48 Hertz. Split under tower chord position. This is because that's the position I pulled this video information off of, into AV3. That connection down here in the bottom right picture. That's the input I use. Okay, now the OSSC is doing two things for me. It's taking that 4:3 ratio. I'm keeping it in a 4:3 ratio, and it's going to change the sync signal into something that's usable for the display. I need a 48 or 60 hertz sync signal, whatever sync is available for the smartboard display. Older displays, as I mentioned, monitors like in medical equipment and computer monitors could make use of that 25 kHz horizontal sync, but monitor devices do not. So it's making that signal usable for me, and then it's going to upscale it, which is the most important thing, to a 1280 by 960, which is a 960p signal at 48 hertz. And then that's piped out over HDMI into the smartboard, and that's how I do it. I've got some additional information that I include in these slides as far as the main menu, so video and processing. My settings for there. Again, you see these offsets on here. If I need to change the gamma, I would do it through those signals to increase the brightness or color saturation on the saturation. I know I said saturation multiple times earlier. Saturation. Yeah, you could do it through those through those settings there. Like I said, here you go, 480p. All these different settings. If you need to back up and freeze at any point to look at them, if anybody was going to do anything different, there you go. You can do the same. Okay. Some of these are just device settings, but is what it is. Pause the video if you needed it during any point in that section. And then, of course, the rest of this is that I could go through, just kind of goes through like the setup, because I got 2 rooms where I'm using multiple keys and stuff. I also got a something called a dialer and the SCT for the ETVS, different types of computer devices that do different things piped over to a smartboard that'll eventually make them interactive through the smartboard as well, but neither here nor there. Okay, so that's going to do it for this this short portion. There goes the slides. There you have it. And anything I could do to help my students learn, you know, that's my job. So if you found this video interesting, let me know in the comments below. You know, it's kind of introducing you into one of the things I kind of teach around here at the schoolhouse I work with. And you know, yeah, just let me know. If you're new to this channel, please consider watching other videos, mostly repair videos. Subscribe. You're here, why not? Go ahead and subscribe. That all being said, thank you for watching. Take care and goodbye. Bark.